Okay. Is it available now?
Okay, student, can you help? Can you answer Professor Abraham questions? Because yes, I can see it now. Very good. Slide 19.
Yes. Okay. Right. So we want to continue on the subtopic on speed of sound. We have already looked at the overview of what is normal shock wave, as well as the basic normal shock equations. So we already look at the 5 equations that are normally being used to solve normal shock problems. Okay, so right. Now we would like to look into the speed of sound, how speed of sound is relevant in our topic, compressible flow. We know that common experience tells us that the sounds travels through air at some finite velocity, right? Because sound also travels at at a high speed. For example, you see a flash of lightning in the distance, but you hear the corresponding thunder at some later moment, right? So because light travel much faster compared to sound, all right? So what is actually the physical mechanism of the propagation of sound wave? The moment you see the lightning, you see the flash, and then the moment you hear the sound of the thunder, right? So how does the mechanism, what is the physical mechanism of the propagation of sound wave from the source to your ear? And how can we calculate the speed of sound? What properties of the gas does it depend on? Those are some questions. The speed of sound, which is extremely important quantity, which dominates the physical properties of compressible flow. And hence, the answers to the above, the number 1, 2, and 3 just now, are vital to our subsequent discussions. Okay? So the physical mechanism of sound propagation in gas is based on molecular motion, right? So these energized molecules, so the molecules that vibrates, okay, are moving about in a random fashion. So imagine it is from the source here, from a speaker, it travels in a random fashion until it reaches your ear. Okay, it goes into your ear. So they eventually collide with some of their neighboring molecules. The molecules collide to each other and transfer their high energy to the neighboring molecules. So in turn, so these neighboring molecules eventually collide with their neighbors and transfer energy in the process. So energy is being transferred from one molecule to another molecule, one molecule to another molecule until it reaches your ear. So this is sound. So and the propagation of the energy wave is simply the propagation of a sound wave. So we call it as a sound wave through the gas. So now let us explore and derive equation for the speed of sound in gas. So in our case, it is in air, okay? And consider a sound wave propagating through a gas with a velocity A, right? So the velocity A over here, as sketched in this particular figure, a sound wave propagating with velocity A into a stagnant gas. So we have station 1 and then we have station 2. So the other figure here, a stationary sound wave in a moving gas, the upstream velocity relative to the wave is A. So one sound wave propagating with a velocity A on this direction and another stationary sound wave in a moving gas, the upstream velocity relative to the wave is is A. Okay, so let us read through this. So you hoop with the sound wave and writes with it, and moving as well as stationary sound wave, these two analogous pictures, only the perspective is different. Okay, so you can see here where in station 1, in this particular case, in case 1, where you have at station 1 is the pressure, temperature, and the density. And at the station 2, where the sound wave propagating into the velocity A into a stagnant gas, where we have at station 2, where we have the additional pressure there, P plus dP, additional temperature, temperature plus delta T, and additional density, density plus delta d rho. At the same time, over here we can also write it a stationary sound wave in a moving gas. The upstream velocity relative to the wave is A, where you have the P in station 1 and P plus dP in station 2. Similarly here, temperature, density, and the velocity itself, where it is adding up. Okay, where we can see here from figure B, it is similar to the picture of a normal shock wave shown in this particular figure, in this particular sense. So please take note that the sound wave in figure B is nothing more than infinite weak normal shock wave, right? So you can imagine that it is since it is moving at a relative speed. Okay, so we can picture it as a normal shock wave as this figure. So note here, the flow through the sound wave is both adiabatic and reversible. Okay, so the flow is isentropic. Because of similarity, we can use previous formulation in shock wave condition. Right? So the one that we have already gone through before, and we can see that the movement of the stationary sound wave in the moving gas is similar to a shock wave case. When we apply continuity formulation, right, where we know that at station 1, density at station 1 times the velocity at station 1 will be equal to the density at station 2 and velocity at station 2, right? So we put up the expression there, okay? And for the density, P, since at station 1, the density is actually times the U1 is A, right? And at station 2, U2 is now dA, okay? A plus dA. So you rearrange that, right? So you will then get solve for A and neglect the two differential, right? You get A equal to negative density rho times dA over d rho, okay? Okay, where density 1 equal to density 1 U1, which is equal to A1 rho 2, which is equal to the rho plus d rho, and U2 equal to A plus dA. And then this equation will become this. So applying momentum formulation, right? So when you apply momentum formulation, where we have the P1 plus rho 1 times the velocity squared 1, which is equal to the P2 plus rho 2 U squared at station 2, right? So you replace U1 as A, okay, and U2 as A plus dA, right? So and rearrange, you will then get this expression, okay? Right. Substitute dA into A equal to minus density dA over dP, d rho, okay, you substitute dA and then solve for A squared, we will have this, A squared equal to dP over d rho, and previously sound wave is isentropic, so hence we can write the equation as A, which is equal to the square root of delta P over delta rho, entropy, for calorically perfect gas. We know that P1 over P2, which is equal to the ratio of the density at 1 and 2 to the power of gamma. Right? So solve and neglect the two differential and use the same method. And from there, from the equation, we have this, P, the pressure over the rho, the density to the power of gamma, which is equal to constant, right? Which is equal to C, where P equal to C rho to the power of gamma. And differentiate the equation with rho, and you can get this expression and substitute C, which is equal to P, substitute C here, C, which is equal to the pressure over the density to the power of gamma into this equation. You can then get this expression. All right. And then you substitute it back to the equation. Equation A equal to square root of delta P over delta rho. And then we have this expression, and knowing the equation of state, which is P equal to rho RT, then we rearrange it, replacing P over there, P over rho, you will then get RT. So basically, the speed of sound A, which is equal to the square root of gamma time the gas constant R time the temperature. And the speed of sound at standard sea level is useful to remember, and it is 340.9 meter per second or 1117 feet per second, right? So that is basically the speed of sound at sea level. We are talking about sea level, right? So recall the previous compressibility equation for fluid, where tau s equal to minus 1 over we call it as a V here, nu, where delta nu over delta P, and knowing specific volume, volume per unit mass, where V here, small v equal to 1 over the rho, the density, then the equation can be written as follows, right? And we can also recall back earlier, where we can then write the tau s equal to the 1 over rho A squared, okay, and rearranging that, where in this condition, right, so we put out all the condition for the rearranging for the V, which is equal to 1 over rho, and which is equal to rho to the power of minus 1, okay? So this equation relates the speed of sound to the compressibility of a gas. And the lower the compressibility, the higher the speed of sound. So recall incompressible case where fluid tau s equal to 0, hence the equation states that the speed of sound in a theoretically incompressible fluid is infinite. In turn, for an incompressible flow with finite velocity v, the Mach number, which is equal to m equal to v over a, is 0. V is the finite velocity over the speed of sound equal to 0, right? So finally, in regard to additional physical meaning of the Mach number m, we consider a fluid element moving along a streamline. So duration so the ratio, so not ratio of kinetic and internal energies. So we have the kinetic energy over the internal energy per unit mass, which is equivalent to E here, can be written as follows. So ratio of the kinetic energy to the internal energy per unit mass. Okay, so we then rewrite what is internal energy per unit mass, which is CVT, right, which is equal to the rearranging again, translate CV equal to R over gamma minus 1, and then you replace it to a speed of sound, and then finally you will get this expression. Okay, so where gamma times gamma minus 1 over 2 times the Mach number squared, which is equal to the kinetic energy ratio over the internal energy per unit mass. So hence, we see that the square of the Mach number, the square of this Mach number is proportional to the ratio of the kinetic energy to the internal energy of a gas flow. So again, it depends on the type of gas, right? So in other words, the Mach number is a measure of the directed motion of the gas compared with the random thermal motion of the molecules. So I just want to repeat here, where the Mach number itself is a measure of the directed motion of the gas, because it is the kinetic energy of the molecules over the internal energy per unit mass of the molecules. Okay. Now, let us look at a few examples. There are a few examples taken from the Anderson book. I did not take all examples. Okay, I just pick up a few so that we can really appreciate what's going on. Example 2.1. Okay, consider an airplane flying at a velocity 250 meter per second. Right. So what you need to do is basically to calculate the Mach number of the aircraft if it is flying at a standard altitude. The first condition at sea level, and then we want to calculate the Mach number at 5 kilometer altitude, a little bit higher, and then another altitude of 10 kilometer, roughly around 33,000 feet. Okay, so we are going to get the same Mach number for the different altitude, or we are going to have a different Mach number? How to approach that? So I really encourage all of you to do it by yourself in terms of trying to get the correct answers, just a simple exercise, right? So at sea level, so you have to refer to the Appendix D. I just take a snapshot of Appendix D, okay, from the Anderson book. It's just a standard data, for standard atmosphere, right? So we have a column of altitude, right, as well as temperature, pressure, and density. So in this case, when we want to use the information at sea level, we take at 0 meter, meaning that at the sea level where we have the temperature reading, the T free stream temperature at sea level is equal to 288.16 Kelvin. You can put 288.16 over there, or you just leave it as 288 Kelvin. So we know already to find the Mach number, you need to first find the speed of sound at the free stream, A free stream, which is equal to the square root of gamma times the RT, and we know also the gas constant for air is equal to 287, right? And we have the gamma value for air, which is 1.4. So we put the number 1.4 there, times 287 times the temperature at sea level from this data, okay, 288.16. So you will eventually get the speed of sound to be 340.2 meter per second. Okay, And then to find the Mach number, free stream Mach number, so you will, since the aircraft is flying at 250 meter per second, so you just put the value 250 meter per second over there, divided by the value that you obtained earlier for the speed of sound, then you get the equivalent Mach number at sea level, 0.735 Mach number. Alright, I hope you can try to get that simple calculation correct. Okay, and then what happened at 5 kilometer? Similarly, at 5 kilometer, you then have to find the values altitude at 5,000 meter, which is equal to 5 kilometer. You get 255.69 Kelvin, right? So you can use 255.69 Kelvin from this table, right? And again, similarly, from the previous A section, you will use the same equation because gamma is the same for air, and then R is the same for air, 287. You just times the 255.7 and square root the answer to get 320.5 meter per second. And finally, you get a slightly increased value of the Mach number, 0.78. All right. Okay, and then we continue to find the Mach number at 10 kilometer. And what is the value of the free stream temperature at 10 kilometer? So again, go back to the appendix D, look at the 10,000 meter over there. You use this number 223.26. Again, some students said, why we just take 223.3? Yeah? Why can't we use 223.26 Kelvin? And the answer is that you can use the exact value here given in the appendix D, 223.26 as the value over there. This is coming from Anderson, so maybe he just rounded up to the nearest decimal. Okay, but for accuracy you can maintain. You can maintain to take up 223.26, and you see the final value is not that far away from this answer. Okay, so following the same approach, the same gas constant, the same gamma for air, you get 299.5 meter per second for the speed of sound, and then eventually you get 0.835 of the Mach number at 10 kilometer. Okay, what does that mean? From at sea level, you get 0.735, and then at 5,000 meter, right? You get 0.78 Mach number, and then at 10 kilometer you get 0.835 Mach number. So the Mach number increases because of the temperature. The temperature is different at 10,000 kilometer compared to 5,000 kilometer, 5,000 meter, and at sea level, which is much hotter, 288.16 Kelvin, right? So note here that the Mach number used here is the free stream Mach number. And when we refer to the Mach number of an aircraft or airplane or any other object in flight, it is the velocity of the object divided by the free stream speed of sound at that altitude. Okay, so that's what we mean by when we highlight this is the Mach number. The Mach number of the aeroplane is, in this example, obviously depends on the altitude at which it is flying, because the speed of sound is different at different altitude because of the temperature is different. So in this example, an airplane velocity of 250 meter per second will correspond to a Mach number of 0.735 at sea level, but a higher Mach number of 0.835 at an altitude of 10 kilometer, even though the velocity of the free stream remain the same. Velocity still 250 meter per second, but the corresponding Mach number is increasing because of the different temperature of air that resulted to a different speed of sound. Okay, I hope you can try to get the correct answers, A, B, and C, for example, 2.1. Let us move into the next example, example 2.2. Okay, in the textbook, it is called example 8.2. Consider the flow properties at a point in a flow of air being pumped into a reservoir. Okay, where the temperature is 320 Kelvin and the velocity is 1000 meter per second. Right, so you have the T here, temperature, and the velocity of 1000. You have to calculate the Mach number at this point, right? At this point of airflow pump into a reservoir. So using the same formula, where we have the to find the speed of sound, we are using air. Remember, just be careful. This time they still use air 1.4, 287 times the 320, which is the temperature. Because it's given there. It doesn't mention it is at the sea level or it is at 5,000 meter or 10,000 meter. It's given a temperature there. 320, just use this value to get the speed of sound, which is 358.6 meter per second. And then you will then obtain the Mach number at this particular point, where velocity 1000 divided by 358.6, which is correspond to the Mach number of 2.79. Okay, so you can see here this simple calculation is given to demonstrate the Mach number as a local property of the flow. So it is slightly different from the one that we had earlier at different altitude. Okay, so it varies from point to point throughout the flow field, and this is contrast with the free stream Mach number calculated in the earlier example, example 2.1. So a purpose of these two examples is just to illustrate the two uses of Mach number, when it is where you need to find the different speed of sound because of a different value of the flow properties, the temperature at a different altitude, or in this particular case, it is used to find Mach number as just at that one particular point. Okay, I hope you can see the difference between the two examples. Let us move into example number 3, where in this example, you have to calculate the ratio of kinetic energy to internal energy, right? So we already have that expression before. So we have the value of the internal energy, kinetic energy, divided by the internal energy per unit mass, right? Where the Mach number is given as 2, right? So you put up the expression. So in this particular case, we have airflow. So gamma in this case is still 1.4, right? So 1.4 times 1.4 minus 1, which is 0.4, divided by 2 times the Mach number in the A case is 2, which is squared. Then you get 1.12 for the first case, right? When Mach number is 2, the ratio of the kinetic energy to the internal energy per unit mass is equal to 1.12. If it is 20, okay, you put the same number there, same gamma value for air, and you solve the equation, you will get the ratio of kinetic energy per internal energy per unit mass equal to 112, compared to 1.12 for Mach number 2 and 112 for Mach number 20. Okay. Note also over here, examining these two results, and we see that mark number 2, at mark number 2, where the ratio of internal energy, kinetic energy to the internal energy are about the same, whereas at the large hypersonic Mach number 20, the kinetic energy is more than 100 times larger than the internal energy. So you can see here is a ratio of kinetic energy to the internal energy. It is nearly 1 to 1.12 to 1, compared to here where it is 112 to 1. So is 100 times larger than internal energy because of the high velocity. We call it a hypersonic Mach number. This is one characteristic of hypersonic flow, high ratio of kinetic energy to the internal energy. Right? So the higher the speed of the vehicle going through the air, we will experience a larger ratio of kinetic energy to the internal energy. Okay, so this is the another example how to look at a different Mach number applications, right? Let us move into another example. Okay, example 2.4, right? So try to consider a long tube. So you have a long tube of a length of 300 meter. Okay, 300 meter. The tube is filled with air. Okay, this time is still air. Remember, air gamma is 1.4. The gas constant is 287. Right? At a temperature of 320 Kelvin. Right? So it's also given the temperature 320 Kelvin. A sound wave is generated at one end of the tube. So at one of the tube, we generate a sound wave, and they want to measure how long will it take for the wave to reach the other end. From point 1 to point number 2, when sound is being generated, the sound will propagate to reach the end of the tunnel, which is 300 meter in length. We assume the same temperature in the tunnel, okay, because we fill the tunnel with air at a constant temperature of 320 Kelvin, right? So this is assumption. If the temperature is not the same, if the temperature over here at the inlet is not the same at the outlet, we cannot use this expression, right? So it's something different. Okay, so solve that for the speed of sound first. Okay? You put the numbers in, you will get a speed of sound to be 358.6 meter per second. Okay, letting the L, the length of the tube, and time for the sound wave to traverse the length L. So we have the time equal to the length over of the speed of sound. Okay, we will get 300, since 300 meter, and divided by the speed of sound. So you will get the time taken, how long it will take from the point A, the inlet of the sound wave, to propagate to the other side of the tunnel, and the tube, which is equivalent to 0.837 seconds, less than 1 second, right, to travel to 300 meter. Okay, so that is the first case, first condition. In another condition, we now fill the tube with helium, no longer air, right? So if it is air, the gamma is 1.4. If it is helium, now the gamma become 1.67. At the same time, the gas constant for helium is not the same as air, 287. The gas constant for helium is 2078.5 joule per kilogram Kelvin, right? So you have to look at what kind of gas being used. If it is argon, it is different value. Now it is helium. If it is a different gas, it is a different value of the gamma as well as the gas constant. Right? So putting the numbers in 1.67 times 2078.5 times 320 temperature, right? 20 Kelvin, square root it, and you will get a speed of sound to be 1054 meter per second, which is much faster than the air. Okay, so then you will get the time to become 0.285 seconds. So you can imagine, if it is filled with air, it takes 0.837 seconds. Once it is being filled with helium, it becomes 0.285 seconds, which is much faster, and 4 times faster. Okay, note that the speed of sound in helium is much faster than in air. Okay? At the same time, temperature for two at the same temperature, and for two reasons. Number one, the gamma for helium is larger, 1.67. For air is 1.4. And more important, helium has a molecular weight of 4, which is much lighter than air, which is molecular weight of air is 28. Okay, because of the gas constant equal to molecular weight, the universal gas constant R divided by the molecular weight of the gas, the same value for all gases, then gas constant for helium is much larger for air. Air is 287, for helium is 2000. And that's the two reasons why the speed of sound will travel faster, much faster than the travel in air. Earlier, before we take a break, I already highlighted that we have a facility of we call it as a gun tunnel. Okay, it is around 4 meter length. So at first we use compressed air. We use compressed air, which uses a value of gamma 1.4. The R is 287. But after a few iterations, now we are using helium. We are using helium, compressed gas helium, for our gun tunnel to release the compressed air into a long tube to push the bullet so that it travels at a much higher speed. If we want to make it slower, we can then go back to just using a compressed air. All right, so it makes a lot of difference. You can see that the time taken to travel a 300 meter tube is 4 times faster if you are using helium. Okay, so we also experience this at our small gun tunnel, and we managed to get the velocity as required to be compared as at the actual bullet traveling from a gun barrel. So this is another example which is very good to be to really understand what's going on. And from this example, you can see that using a different type of gas will resulted to a different Mach number, and of course the properties of because of the properties of the gases are different, you will get a different speed of sound. Okay, so let us stop there.